Hi everyone, my name is Hongyu Liu. I'm going to present our paper, Voucher in situ failure diagnosis. This is a joint work with Sam, Professor Zhang, Professor Huang, and Professor Liu. This work was initiated and partially conducted while Hongyu Liu and Tongming Liu were at the University of Texas at San Antonio. I guess everyone will agree that software exists in almost every aspect of our daily life. In a word, software benefits everyone when they are working correctly. However, they may cause issues in case of software failures. The bug may cause serious problems such as program crash and data corruption. Even worse, the bugs may be exploited by attackers, causing security problems. However, when a bug occurs, not every user is willing to send the bug report. So developers cannot know and fix this bug, which may happen again. Even the bug report is sent to developers, they may not reproduce it due to some execution environment problem. So it's difficult for developers to fix the bug. Based on a recent report, software failures has caused 1.7 trillion financial losses in 2017 and affected 3.6 billion people. Researchers propose many techniques to debug failures. Among them, there are two popular work, Snorlax and REPT. Snorlax proposes a hybrid analysis to diagnose the root causes of concurrency bugs, relying on coarse-grained interleaving information that is collected with advanced hardware Intel PT. It could diagnose concurrency issues automatically. However, they can't diagnose the sequential bug or multivariable issue, and it needs to collect multiple traces from users. REPT also collects similar information such as control flow information and code dump. After that, it employs a new binary analysis approach that combines forward and backward execution to recover data flows. Based on their paper, they could recover the data flow up to 78,000 instructions. Since they already constructed the data flow, it allows the offline debugging based on that. However, the data flow can only be recovered around 90% accuracy. If the faulty state cannot be recovered, they cannot identify the root cause. Besides, they also share one common issue, the privacy concern. Code dump may contain users' sensitive information, such as passwords. To overcome the privacy issue, the ideal workload would be like this. User installs and use a program. When something is wrong, the diagnosis will be invoked automatically on the failing process. The user may just relax for a few seconds, like drinking a cup of coffee. After a while, the system will report the root cause to programmers so that they could further fix the bugs. In this ideal situation, only the root cause will be sent to software vendors, not memory code dump or execution records, so that normal users do not need to worry about the privacy issue. Also, the proposed work should be able to overcome the effectiveness of existing systems. Automatically, failure diagnoses are suitable for both in-house testing and deployment setting. This is a dream for programmers. Now I'm going to present how our work Voucher achieves this dream. Voucher relies on the deterministic record and replace system iReplayer. People can replace iReplayer with other record and replace systems, as long as these systems can deterministically reproduce the bugs. Voucher proposes a hybrid analysis within replace. it follows the reverse order where the bug comes from. When a bug happens, it first captures the signals such as zigzag, zigbot, and so on. Inside the signal handler, Vultr identifies failing instructions or registers using binary analysis. It then identifies failing addresses. After we know the failing addresses, we can collect the data flow on that address. However, binary analysis may not provide enough information. Vultr consult the record and replace system to collect more data. For concurrency issues, Vultr also performs a happen before analysis to prune unnecessary information. In the end, Vultr conducts the root cause analysis and generate a bug report. So I will explain the details regarding these steps. When a bug happens, like we use GDB to debug, the first step is to identify failing instruction. For zigzag or zigFPE errors, the failing context points to the failing instruction. But for zigbot, the failing context points to the instruction that invokes a bot, but not the reason of a bot. For example, there's an assertion failure in a program, like assert x is not equal to 0 and y is not equal to 0. The assembly code is shown in this figure. From the calling context, we can only know the function assert fail is invoked. Basically, when condition fails, it jumps to call this function. Vultr follows the binary level control flow graph to identify all possible branches that can jump to this code block. So in this case, there are two variables, x and y. Binary analysis cannot determine which one caused the failure. Vultr installs breakpoints on these two instructions and identifies the failing branch within identical replace. For example, in this case is x, where the GE instruction in the right rectangle is taken. The test instruction sets the register flags using the values in register EAX. So EAX is the failing register. When we know the failing register, we would like to know where the value in this register comes from. Therefore, the second step is to identify the failing addresses where the value is loaded from. First, Vultr uses binary analysis to identify all load instructions to the failing register. In this example, is the move instruction. The source operand is the memory address 0x to 00b to 0 RIP. Since RIP is the address of the next instruction, the failing address can be computed. But if RIP is a general register, Vultr utilizes another replay to collect the value of this register so that the address can be computed. Once the failing address is determined, Vultr installs a word point on that memory address and collects memory address within identical replace, including the calling context, values, signalizations, and so on. Vultr does not modify the binary code. It relies on hardware to instrument the program. Breakpoint is used to collect partial control flow information, while word point is used to collect data flow information. All this process is automatic. For concurrency bugs, Vultr may collect lots of memory accesses from multiple threads. Since every player records log orders, Vultr analysis that happens before relationship among threads using the log orders. The figure shows an example that the value for address 1 is z in the end, which is set by thread 2. So x assigned to address 1 in thread 1 is not considered. In the end, voucher reports what the failure feature is, and the failure type, whether it's a sequential bug or concurrency bug, and the fault propagation chain, which is kind of backward program slicing. In the report, developer can know what the wrong value is and where it comes from. So they are very useful for developers to fix this bug. The performance overhead for the normal execution is up to the record and the replace system. We evaluated voucher on the Parsec benchmarks and some real applications. The results are normalized to the default version. The performance overhead is less than 2% on average. We also evaluated the effectiveness of voucher on many known bugs. Voucher can identify the root cause for both sequential and concurrency bugs, including stack overflow, non-pointer bugs, divide by 0, and so on. Voucher has two modes. One is I just presented. Another one is to use hardware trees provided by Intel PT if it's supported. So voucher performs the analysis based on the Intel PT trees. The diagnosis time for both modes is around 2 or 3 seconds on average, which should be acceptable by users. To conclude, we present the voucher, which use hybrid analysis to identify root causes. It reports detailed information for developers to fix the bug. The performance overhead is very low thanks to Azure Player, and is very efficient for failure diagnosis. Thank you so much for your attention.